Hi guys, here we go. This is specifically about the Tca cycle or citric acid cycle. This is the cycle. Tca cycle, it starts with the acetyl-CoA here, which is combining with oxaloacetate, and then it's produced citrate. This enzyme, the name of this enzyme here is citrate synthase, and then you have the isocitrate being produced, alpha-acetylglutarate, succinyl-CoA, succinate, fumarate, malate, and oxaloacetate. So these are the metabolites that compose the TCA cycle. Okay. Look here, how many NADH can be produced here. So one NADH here, one NADH here, one NADH here, and FADH2 here. So from succinate to fumarate you have this production. So remember that these are going to be used by several reactions, not only the oxidative phosphorylation, but they are substrates for the oxidative phosphorylation. So the TCA cycle is a very important producer of substrate that is going to be consumed in the oxidative phosphorylation. This you release electrons in the electron transfer chain, and then you have a series of proteins that can carry these electrons and also pump the protons, and then you have ATP synthesis. So one of the functions of TCA cycle is this: produce these substrates that's going to be used in the next phase. But when you talk about NADH or NAD or NADPH and NADP, we are talking about redox metabolism. Okay, so when you see something about redox metabolism, we are talking about a series of reactions that involves also, not only but also NADH, NADP, NADPH, and so on. Okay, so this compound here is very important for the redox metabolism. Okay, see here that we have two CO2 released here. Before the acetyl-CoA, you have the degradation of pyruvate by the pyruvate dehydrogenase complex that also release CO2. That's why CO2 is the opposite of photosynthesis in terms of gas exchange, because it's producing CO2. So if you want to measure respiration in any organism, you can measure the quantity of CO2 being released. I'm not saying that only these reactions of respiration produce CO2. No, there are many, more than 200 reactions that can release CO2, but most of the CO2 released comes from the respiration. Okay. In plants, this is a bit different from the animals. I will explain why. And also, some of these reactions also have in the chloroplast. So what we don't have in the chloroplast for sure is this enzyme here, succinate dehydrogenase, for example, and some of these enzymes here we don't have in the chloroplast. But we say that the TCA cycle can works you have a partial TCA cycle in the chloroplast, but the complete cycle is only in the mitochondria. Okay, and animals don't have chloroplast, so you don't have these enzymes there. So this is completely in the matrix of the mitochondria of animal cells. Okay, you have this is occurring in the mitochondria, but all the enzymes, all the metabolites here can leave the mitochondria. So the malate produced here can leave the mitochondria and go to the cytosol. In case of plants, can go to the chloroplast. So it's not that this cycle is only working in this direction. Okay, sometimes the citrate can leave the mitochondria, the alpha-acetylglutarate, you for sure leave the mitochondria through the synthesis of amino acids. Okay, so the carbon is not really just walking around here. Okay, the carbon in the TCA cycle, it provides substrate for many pathways. We are already seeing this slide, so I hope this is clear for you. The carbon that enters the TCA cycle will not be here forever. So at some point this carbon will leave to the synthesis and be used as substrate to the synthesis of something. Okay, for example, glutamate and glutamine synthesis are very important for every organism, and it depends of the alpha-acetylglutarate that comes from the TCA cycle. Okay, so it's very important that these metabolites leave the mitochondria and go to the cytosol to the synthesis of these compounds. So many amino acids depends on the TCA cycle. But talking about plants is a bit more complicated, okay? So if you want to understand a little bit more about plant Tca cycle, and I hope you can search for this paper, because it's very interesting, and it's a very good paper. So the title already say what I want to say for you, not just a cycle. So Tca cycle is not really working as a cycle. So here you have the conventional mode of fluxes in the Tca cycle as a cycle, as we see in every book, and we were seeing in the previous slides. But in reality, in plants, what happens is that some of these reactions are not really working in the light. Okay, this seems to be specific to light conditions, but not only. Okay, some seeds that do not need light, the Tca cycle also works in a non-cyclic mode. Okay, so for example, here we have the citrate that has been stored in the vacuole of plants, and then the citrate entered the mitochondria, and then you have the transformation to isocitrate, to oxaloglutarate, and then oxaloglutarate leave the mitochondria to the synthesis of glutamate. So here, only part of the Tca cycle is working. Okay, the other part is working for another thing. Okay, the PEP that's gonna be used to assimilate CO2. So this enzyme here is PEPC, PEP carboxylase, phosphoenol pyruvate carboxylase, which produce oxaloacetate. Oxaloacetate can enter the mitochondria, be converted into malate, be converted into fumarate, repair that these reactions here, it can work in both directions. So if you have fumarate being synthesized in the cytosol, the fumarate can also enter the mitochondria, can be transformed to malate, and can be transformed to oxaloacetate, and the other way around also. Okay, so these two reactions here are working in both directions. You're going to see that this ASR can also work in the reverse mode. We're going to see it. Okay, so this is just one example that happens in this plant here, which is important for the nitrogen assimilation, because nitrogen assimilation depends on glutamate, glutamine, and so on. Okay, so this is working to help a nitrogen assimilation in these plants. And we have a modeling study very important that predicted this response. So in the light, it seems like the Tca cycle is working in a non-cyclic flux mode. What means this? It means that the citrate that has been stored during the dark period, it's stored in the vacuole of plants. This is in plants, right? And enter mitochondria, and then the mitochondria is converted to oxaloglutarate, and then glutamate and glutamine. So this part of the cycle is working to this, and part of this cycle here is working to accumulate or malate or fumarate. Okay, so the cycle, we say that the cycle is broken. So you have a broken flux mode in the light. Repair that in the dark, you can have the cycle working normally. Just because here you have some enzymes that are inhibiting the light. Okay, we're going to see these enzymes. This is the reason why this cycle is not working as a cycle. But the things become more complicated when we see other microorganisms. For example, you have here in bacteria that you have a different kind of Tca cycle. So based in acetate, the acetate can be degraded to produce acetyl-CoA, and then you have, let's say, a new start of the Tca cycle. So between these reactions here, from succinyl-CoA to succinate, you can have incorporation of acetate, and then you have acetyl-CoA being released. Okay, and then the acetyl-CoA combined with oxaloacetate is used by the citrate synthase to synthesize citrate. Okay, so this is a different type of Tca cycle. And actually, talking about different ways that the Tca cycle can occur, I recommend you to check this paper. It's a review about how the Tca cycle can be found in different organisms. And here is specifically, not specifically in cyanobacteria, but you have many organisms here. So the conventional Tca cycle is this, okay? But repair that you have many reactions that can occur in both directions. So this makes the thing more complicated to understand in which way the Tca cycle is working, because it can go forward, can go back. Okay, and here you have at least six types of modes that the Tca cycle is working. So some are complete Tca cycle short, which is this one here, the 6. You have the 2, the 1, the 3, the 4, the 5. I mean, you have different combinations that can have a different mode of flux in the Tca cycle. Just check this paper. You're going to see this more in detail. And perhaps the most interesting thing is that we have a reverse Tca cycle. So this evidence is very old. It's from this guy here, from Bob Buchanan, Daniel Arnold, and Evans. It was first published on 1966, and then Bobby wrote a review on 90 about reverse Krebs cycle, which occurs in some bacteria to fix CO2. So some bacteria can fix CO2 instead of releasing CO2. Remember that I showed you some reactions that release CO2. So if this reaction occurs in the opposite direction, it means that the CO2 is going to be incorporated. Okay, so some bacteria do that. So they can fix CO2 by reversing this reaction. That's why we say reverse Tca cycle. Just that this mini review here is very short. It's very interesting to see. Bob is a very good researcher. And how these systems work, the reverse citric acid works. So for example, you have, in normal you can see the carbon coming here and so on. But here you are seeing the arrows are in the opposite directions. So in this case, if you have succinyl-CoA being converted to alpha-acetylglutarate and alpha-acetylglutarate to isocitrate, instead of having CO2 being released, you have CO2 being fixed. Okay, so and another possibility is that acetyl-CoA can also be converted to pyruvate, and pyruvate to phosphopyruvate, and then oxaloacetate. And here you have more 2CO2 being fixed. So this is not a photosynthesis because there is no need for light, okay? But it's a way that bacteria found to assimilate CO2, okay? So far, as far as I know, we don't have any evidence that this can occur in other organisms, but if you find, please let me know, okay? We have here two, you see, oxaloacetate to malate, fumarate, succinate is the opposite direction of the conventional Tca cycle. But how the Tca cycle is regulated? So there are many things, from allostatic regulation, transcriptional regulation, post-translational regulation, and protein-protein interaction, as far as we know, and there are many other to be discovered. This is what is included in the book, so you know that the book is not always updated. The most updated things are the papers. For example, the pyruvate dehydrogenase in plants, for example, are inhibited in the light. So this is why this cycle is not really working as a cycle in the light, because this enzyme here is inhibited in the light by phosphorylation. Okay, pyruvate dehydrogenase can also be blocked by ATP. It means that if the oxidative phosphorylation is producing too much ATP and is not consuming this in the other reactions, the excess of ATP is going to block this reaction. Okay, so it's a kind of feedback negative regulation. And in the other way around, if you have AMP, which is can be used to the synthesis of ATP, because AMP can be converted into ADP and then ATP. So if you have a lot of AMP and then you have activation of this enzyme. You see many compounds here can activate or deactivate this compound. For example, here NADH, succinyl, CoA, citrate, these are all allostatic regulation. Okay, calcium is also important for the regulation. You see that can activate 3 different enzymes, for example, pyruvate dehydrogenase complex, isocitrate dehydrogenase, and alpha-acetylglutarate dehydrogenase. Okay. So you see here that you have many dehydrogenases. These dehydrogenases are very important to produce NADH. Okay, and the succinate dehydrogenase, instead of producing NADH, can produce FADH2. This is going to be used in the next phase. So this is just a simple examples of allosteric regulation of the Tca cycle. But we have many others. For example, here you have in plant Tca cycle, each enzyme, how they are regulated. And actually this paper is from 2013, so it's not really updated. But for example, one enzyme can be, for example, let's talk about aconitase. Can be regulated by phosphorylation. Redox regulation is highly sensitive to oxidative stress and also nitric oxide. For example, isosaturated dehydrogenase can also be regulated by phosphorylation and redox regulation. So for MEDH is even more complex. So phosphorylation, redox regulation, acetylation. Many enzymes, and one enzyme can be regulated by different ways. This is just post-translation modifications. You can have also transcriptional regulation. So the regulation of the Tca cycle is very complex. For example, in plants you have, I told you that the respiration of plants is lower compared to the dark conditions. One of the reasons is because when you turn on the light or turn off the light, you can see you have an increase in the activity of fumarase. So this is the fumarase activity. When you turn the light on, the activity decreases. Okay, so these papers here describe that this system is related to the phytochrome A. So when you have dark, you have more activity. So it means that the Tca cycle is working you have higher fluxes through the Tca cycle, at least in this reaction under dark conditions. And for example, one of the mode of regulation is the redox regulation. We are going to see redox regulation many times in this course. You have already seen sometimes because it's a very important point of regulation of metabolism. For example, here you have the citrate synthase case. The citrate synthase have two monomers that can combine together. And here you have the inactive dimer, which you have this disulfide bond here, and thyrodoxine can cleave this bond. When you cleave, the protein becomes activated. So then you have activation of the enzyme by the thyrodoxine. Remember how the thyrodoxine system works. So you have energy from or the light or the NADPH. This NATR is a protein that reduces the thyrodoxine, and the thyrodoxine reduces the target enzyme. In the case here is citrate synthase. It means that for these things here happen, you need this here, NADPH or NADH. Okay, so the energy that is in this compound here is used by this NATR protein to reduce thyrodoxine. So thyrodoxine can only works when it's reduced, because thyrodoxine reduced can then activate and target enzyme. In this case, is reducing the target enzyme. Okay, so this is redox regulation. Remember that I say NADH and NADPH is very important for the redox metabolism, so that's why. Okay. Another thing that is in plants, we have also this paper showing how the Tca cycle is regulated. This is from my PhD. We have shown that these two enzymes here are inactivated by thyrodoxines, and some of the enzymes in the cytosol are activated, and these enzymes here are also activated. So remember that the Tca cycle is not working as a cyclic mode in plants, and one of the reasons is because thyrodoxine is activating this side here and inactivating this side. So these also explain why respiration is inhibited in the light in plants. So take-home message. Tca cycle is important to provide substrate for not only the oxidative phosphorylation but also many other compounds like fatty acids and amino acids. Succinate, NADH, and FADH2 are substrate of the oxidative phosphorylation that are produced in the Tca cycle. It seems that, it seems that the Tca cycle is not working really as a cycle in the light in plants, and that Tca cycle is regulated by diverse transcription and post-translation regulation mechanisms. Okay, so make it at home. This please, we talking about Tca cycle regulation mostly in plants. Some of these regulations also occurs in other organisms, but to have a clear idea about how this Tca cycle is regulating other organisms, please describe briefly how these Tca cycles regulate in animals or microorganisms or whatever, not in plants. Okay, because plants I have already told a lot. Again, the same thing, each answer should have a maximum of 400 words, not more. Okay, and so we have two answers that was kind of copy paste from the internet. I prefer that you give your own words. I'm not looking here for a perfect answer. The aim here is to make you write. Okay, it's an exercise of scientific writing. This is one of the aims, and the other aims is like to I get what you don't understand, and then I can make a video also to explain you the unclear things. Okay, bye bye.